No question. Actually, I wanted to review homework 4, but I forgot to bring the files. we can review homework 4, your submission at next class. Yeah, this time all students submitted a homework. Good. Yeah, we talked about the switched capacitor integrator a little bit. So switched capacitor integrator is a basic building block. Integrator, continuous time integrator, RC integrator. This is a single-ended version. Yeah, if we apply input here, yeah, because of negative feedback by this capacitor, this becomes virtual ground, right? This is actually reference. It may be 1.65 volt. Okay, here. So AC is 0. So this will be 0 volt, right? Because of negative feedback. So then this current will be yeah, because this current is 0, all the current will flow through this capacitor. Then there will be some charges developed there, right? Because of this current. Then my output voltage here will be capacitor voltage actually. This capacitor voltage will be okay, this will be my output voltage, right? So if I change this one, general sinusoid one, exponential ST, then integration will be changed to 1 of S. So my VOT will be some VOS component, which is yeah. So this will be something like that. Right? Oh, yeah. So there may be some VS term here. There's a frequency component. Yeah, there should be a V in S. V in S. So if my V in T is V in frequency component times exponential ST, my VOT will look like that, right? So my transfer function is just this part, which is VOS, right? VOS, yeah, that's a VOS, divided by V in S. So in this continuous time, say if I change that one in sinusoid, if my V in T is some V in J omega exponential J omega T. So in this case, my S is changed to J omega, just steady sinusoid, right? Then, yeah, my output will change. My output voltage will change minus J omega RC V in J omega exponential J omega T, right? Yeah, in this case, my transfer function will be so this is a continuous time integrator. Yeah, Bayesian shift is what? Bayesian shift is it plus 90 degrees, right? So magnitude is just proportional to inversely proportional to omega. Phase is constant, right? Looks like 90 degrees, right? Yeah, which is half pi radian. Yeah, this is just a continuous time integrator. We want to change it into a switched capacitor integrator. That resistor is replaced by a switched capacitor. Yeah. See. Then let's see. So I have my switched capacitor here, that resistor part. Okay, this is my switched capacitor integrator. So feedback capacitor remains the same, right? The resistor is replaced by a switched capacitor. Yeah, let's change this one. My switched capacitor, let's just say, it's, let me make switches here. So C1 is my switched capacitor. Okay. For simplicity, we just assume this V in T is DC. Yeah, this is 1.65 volt, right? This reference point. So, for example, this is 1.75 volt DC. Then, during by one phase, for this op-amp, let's talk about the by one phase. Left switch is on. This is turned off, right? Then what will be this voltage? We assume this op-amp gain is very large. Then because of negative feedback by C2, this voltage will be 1.65 volt, right? So there are some charges will remain there. Because this current is 0, this current is 0, because the switch by 2 is turned off, Q2 remains the same. Q2 is a constant, doesn't change with the time. So PO is a constant during by one phase, right? Okay. Yeah, in here, because the by one switch is turned on, this capacitor voltage will be charged to 0.1 volt, right? The voltage difference. Okay. Then, yeah, assume initially this VO Q2 is 0. I assume this VO is, then this VO is 1.65 volt initially at T equals 0. This is just the initial condition. Okay. So let's change it to by two phase. Yeah, this V in T 1.75 DC is isolated, right? So this C1 is charged to plus 1 volt here. So yeah, this phi 2 is turned on, and then oh, this is on. So at t equals 0, VO was 1.65 volt. Those Q2 was 0 at the t equals 0, right? Q2 was 0. Yeah, this V on T is isolated because by one switch is off, and then because by two switch is on, you know, just after this by two switch is on, you know, this differential input voltage becomes plus 100 millivolt, right? So then my VOT becomes very large negative voltage, right? See, for example, this will drop. This used to be 1.65 volt, right? This can be dropped to 0 volt, right? Because I have a large positive voltage at the negative input, right? So, you know, so this is 1.65. So this suddenly becomes 1.75 volt, and this becomes 0 volt. Tries to it will drop to 0 volt. Then what the voltage difference between C2 will be pretty large, right? To make that difference, I need a large current flow, right? I need a large current flow. So I need a current to change capacitor voltage, right? Yeah, to change capacitor voltage, I need to change this Q2 value, right? Q2 value. So where does this current will flow through this op-amp, and this current will flow through this op-amp. This current is still 0. So it should flow through here, here, here. So, you know, this charge, the charge on C1 will be C1 times 0.1 volt here, right? There will be minus C1 times 0.1 volt there, right? Yeah, this current comes from that charge. So because this is a positive charge, a large current quickly flows through here. This Q2 charge will change to plus C1 times 0.1 volt, right? This Q2 charge will be minus C1 times 0.1 volt. Very quickly. Then this voltage will go to 0, and this op-amp remains at the virtual ground again. Then no current flows. I becomes 0, and this VOT goes back to 1.65 volt minus C1 times 0.1 volt divided by C2, right? This will be my VOT value at the end of by two phase. Any question? Nope. Okay. If no question, let's continue. At the next by one base, let's go to the next by one base. At the next by one base, my my V in T still remains at the 1.75 volt DC, and then my I1 will be on. Then I have a C1 here, my I2 will be off. Then my op amp remains there, and this VOT is here. This is my C2. Because there is no current, and also negative feedback by C2, this voltage remains at 1.65 volt, right? There is no current. So this Q2 charge doesn't change. This Q2 charge was C1 times 0.1 volt, right? So my VO2 remains at this voltage, 1.65 minus C1 times 0.1 divided by C2, okay? My VOT is a constant during this I1 phase. And this C1 will be charged again to this charge. Charge is 0.1 times C1, this charge minus, yeah, that's a Q1 charge, right? Yeah, next I2 phase, the same thing repeats. You know, this is isolated. I1 is isolated. It's off, right? This is C1 charge will dump. This charge C1 times 0.1 will flow through here, and then, you know, it will be added here, right? So this becomes C1.0.1 times twice, right? Because it's added. This is plus the same amount, right? So at the end of I2 phase, my VOT will be 1.65 minus C1 times 0.2 divided by C2, okay? If I keep on continue it, you know, this VO voltage will go down, you know, stepwise fashion, right? So here's, yeah, there is a I1 phase, I2 phase. See, this is I1 phase clock. Yeah, this is I1 phase clock. This is I2 phase clock is here. Non-overlapping clock, right? No, they should be the same. Then, you know, my VOT used to be, it was 1.65 volt here. Oops. 1.65 volt initially. And then at the end of I1 phase, it changes a little bit. So this is, and then remains constant. I2 phase, it changes again. Yeah, constant. At the end of I2 phase, it changes again, something like that. Okay. The step is here. This step is minus 0.1 times C1 over C2. Okay. So if we just look at the values at the end of I1 phase, I2 phase. So yeah, no, this is here. So I can see there is approximate. This is almost a linear decrease in time, right? So I can approximate. See, what's the slope of this one? This is a t, right? This is period t. This is a clock period t. Okay. So, you know, I can approximate the VOT. This is t equals 0. Where is t equals 0? Oh yeah. Here I assume this is t equals 0. Then just 0.1 C1 over C2 T over T. Is it right? Yeah. So this one is actually my V in. Okay. This is my V. V in T is actually V in T minus 6.15. Okay. Actually my V in. So as T increases, it's just integration of V of T. So in the previous case, it was something like that, right? This is the analog domain integration operation. So this is I can say integration V in T. V in is 0. Actually, there is a minus sign there, right? So here is some negative sign. So let's compare this one. This integration is 1 over S. 1 over S is just integration, right? So I have a C2 there. Then what's R? Yeah, my R is just T over C1, right? This V in 0.1 is my V in, right? So my switched resistor just T over C1 is my equivalent resistor here. Question?